Hello. It's been a while, and for good reason. I've been very busy, but that's not why I'm here. I don't want to talk about that and stall even longer. But I do want to make some revisions to the current 2+2 process because, like, I think it's kind of sloppy right now, and it doesn't really seem to be motivated by the result. I even tried to attempt 2+2, and we'll get to that in a minute because there's actually a reason, and that's why I chose 2+2, not 1+1, 1+0. Actually, I did 1+0, but here, look, this is it came from an exam that I was given. This is a copy. It's an entry-level diagnostic. You can read that if you want. And I believe the 9th question was, it's 2+2. See? Evaluate. And that question confused me. As you can tell, you have to attempt all questions before you can go for the extra credit. Extra credit is not that hard. It's this is the extra credit right here. It's the very bottom one. That's actually this board work right here is the extra credit. So as you can tell, my professor put that in there, but he did not give me the proper information I needed to solve the problem. He didn't tell me that under the group that we're performing the addition on will 2+2 be closed under that group, or what modulus are you going in. Obviously, some of you are thinking well, just assume none of that stuff. Assume that you're not doing modular arithmetic. Assume that your group is closed under addition. You'll get an integer value. But then again, if you see other questions that's surrounded by here, look, I'll read you some. Here's the first question. It's just a simple integral. You're supposed to evaluate it. I mean, well, it's not simple, but the question. The question's nature is simple. One. Here's one. Read it if you want. In fact, here's the whole page. Read it. And here's the page of 2+2. As you can tell, it is kind of out of place. In my opinion, it's the shortest question, but I've been trying to figure that out and see the way to do that. In the current 2+2 process, it's mostly forming on an expansion of 2+2. Well, we're trying to find an evaluation, but I'm certainly not going to throw it out. Here's the actual expansion written out. Funny enough, I don't think this is even correct because if I look back, I made several problems in my recordings. Here's 2+2. What are we going to do from here on out? What are we going to do? Well, we're obviously not going to throw away all of our process. I mean, obviously we're not going to throw away all our progress right here, as you can tell. There's a lot of it. But what we are going to do is we're going to restart. We're going to, first of all, make some postulates and some axioms and some assumptions that we are going to derive. And then we're going to work onto an expansion. And I hope that my professor will see this because I've turned in my exam without doing that question for the class, to enter the class. I don't think you really like that part, but obviously an unattempted question is way worse than you attempting a question and getting it wrong. But it's okay, because we're going to get to the end because I need more time, and I also want to document it because I think it's a very interesting process. And don't forget, we're going to get the time lapses in there because that seems to be all you guys care about and not the actual math, because you guys don't like math that much, I assume, unless you do like math and that's why you're subscribed. But anyways, we're going to keep doing it, and we're going to first this extra credit problem actually caught my eye. I don't even think this is actually not that widely known, but anyways, we're gonna get to that right now. Okay, so what we're trying to do is we're trying to derive this formula. Let me show you real quick. Which is this, which serves as a general formula for the antiderivative of 1 over x to the n+1, not x to the 2+1. So first we're gonna have to derive this. I'm not gonna take this for granted. We're actually gonna derive it. It's actually not even that hard, and it'll actually give you a better understanding of the final derivation. So let's first start. So what we're going to be doing is we're going to be looking at the complex roots of unity of x to the n+1. So that'll go like this. X to the n+1 is equal to 0. All right, so that shows all the roots there. And what we're going to do is we're going to subtract 1. X to the n is equal to -1. And immediately you should see Euler's identity, I believe it is. But essentially it is x to the n is equal to e to the I. All right. All right. But first now I have to define n, because there's going to have to be another number in here. Let's call it k, because it's going to represent all the roots. Because as you can see, there's going to be, when we're doing this, is going to be a unit circle, and all the roots of n are going to lie evenly spaced along the unit circle. And so as we space them along the unit circle, we're going to need another coefficient k to actually space them out. And so k is going to range from, let's get a better squiggly bracket. It's like an inverse squiggly bracket. 1, 2, 3, 4, all the way down to n-1. Oh wait, no, it starts at 0, my bad, because the n-1, because there's n total root. So there's going to be n total k, so starts from 0 equals n-1, so it'll even out. And so then we can have x is equal to e to the I, and the complex root is not going to be k, it's going to be 2k plus 1 pi, and then all over n. So for sake of simplicity, I think we should just like represent this part as like theta, since e to the I theta. So let's just let 2k plus 1 pi over 2 is equal to theta. And so there we go. And if we so here we go, we have the roots right here, all these roots. And now we're going to take out the conjugate pairs and we're going to multiply them to get that multiplicative formula. And do that because of the symmetry along this unit circle. So let's do that. Let's do, like, for example, so e to the I theta and e to the negative I theta. Alright, so we're going to multiply these first. We should subtract probably. So it'll be x minus e to the I theta multiplied just x minus e to the I negative theta. And when we multiply these out, and so for this multiplication, it'll actually be a lot nicer if we don't expand e to the I theta. I actually attempted that previously, and it came out quite messy, but what we can do is we can actually just do x squared minus x e to the negative I theta minus e to the I theta, okay, minus x e to the I theta. And then we can have plus e to the 2I theta. But if we're obviously going to factor on x, so x squared minus x e to the negative I theta minus, and let's actually switch this around to plus real quick. E to the I theta plus e to the negative I theta. I'm done with this. Oh no, I'm done. This is 1. These are conjugates, so we'll multiply by each other. It should become 1. Oh my goodness. Okay. This right here is another identity, so this will be x squared minus x2 cosine theta plus 1. These are the conjugate pairs multiplied by each other, but there's a lot of conjugate pairs, so we're going to have a series, and that series should be quite kind of familiar to you. But first, we got to figure out. It's going to look like this. So we're going to have multiplication. It's going to be multiplicative because you're multiplying the complex roots all together, and it's going to be this on the inside, x squared minus x2 cosine theta plus 1 is equal to 0. And remember, theta is isotropy matters, so don't just think there's not actually anything going on with the cane here. And so, since we multiplied these two conjugates together because of the symmetry along the unit circle, and we have n of these, we're going to need to undo that, so it's going to be n over 2 minus 1. Okay, so that part's kind of confusing. N over 2 minus 1, and there you go. There's the formula right here of the right here. That's the formula. Let me show you. Here it is right here. The only difference is that I'm a professor, he put the x right here, but it doesn't matter. This multiplication. So there we go. There's a formula. And now let's get to the actual part of the actual question. So as a reminder, that question is you're supposed to derive this formula right here, right? And you're supposed to use this right here. Alright, so let's do that real quick. So first, let's understand that we're doing 1 over x to the n plus 1. So let's just represent this. I'm just going to represent this as the big pi, so I don't have to write it all out. Which we're only going to have to use that trick once, but essentially it's going to right now. 1 over x to the n plus 1 is just equal to 1 over the sum, alright? But we can't really integrate that because there's a better way to do this. So obviously we're going to have the integral, the indefinite integral 1 over x to the n plus 1 is equal to 1 to the integral. But not good. But the trick, we can do some summation notation. We can put stuff into the numerator. So let's first do that real quick. So 1 over the sum could be equal to the sum of a x plus b, and yes, we're doing partial fraction decomposition over, and then all the stuff that goes on here. So it'll be just all this stuff. So just call this, well, not a, we're going to be using a later. Blah, 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 blah. All that goes down to here, okay? But first, we're going to have to actually like figure everything out real quick. A, let's first represent cosine theta of a, because it has nothing to do with x, and it just saves me writing time. And we can't really do c because then there's going to be plus c at the end of the integral. So let's first figure out. So this is going to be equal to the sum, and the bounds are the same, of a, big A, x plus b, x, no, there's no x at the b because it's fraction, decomposition. X squared minus x a plus 1, and we're not actually going to count the integral yet, but we can just, so the way this one works is that there's an integral, we can put it, the integral right here and right here, or over there, it's the same thing. So what we're just going to do is we're going to take one of these integrals, we're going to evaluate it. So it's going to be the integral of a of x plus b of x squared minus x to the a plus 1 dx. Alright, squared. So this is going to be x squared minus x squared a plus 1 is going to be equal to x plus a squared x minus a squared. Or no, it's just plus. Alright, and another issue, what am I going to say? I'm not to you guys. Give me a bit, we're going to lock in later. We're going to lock in next school year, guys, for locking in trust. Alright, so there we go, we can have is equal to ax plus b over, and then x plus a squared of 1 minus a squared. You're adding that. So, stepping integral. Alright, let's keep going. We're going to do a u substitution, actually. Let's first let u, and let's do this one, equal to 1 minus, which should not affect the variable, so it will be equal to x plus a. Alright, and so then if we take the derivative, dx is equal to du, and let's just solve for x because we're going to plug this right here. So x u minus a is equal to x, right? So there we go, and this is equal to the integral of a, and then x would be u minus a plus b over, and we're going to have u squared plus 1 minus a squared. Alright, then dx. So let's do this. So this could be broken into, you can factor, or not factor, sorry, you can distribute the a, so it'll be au, u minus, and then we can, since these are, I forgot what the term was, doesn't matter, something in abstract algebra, just kidding, it's actually basic. And then minus, this is supposed to be a, that looks really confusing, of, and it is a little a plus b. These parentheses are placed strategically, and obviously we have the integral, and then we have u squared plus 1 minus a squared, plus 1, we forgot the plus 1. I just always drop that for no reason. Alright, so we can pull this out. This has nothing to do with the actual thing. Actually, we can split this whole integral up into two integrals because it's linear. So this is equal to the integral of a u of u squared plus 1 minus a squared plus 1, and then plus the integral, and it's this part, and let's bring this negative in here, so it'll be b minus a little a over u squared plus 1 minus a squared plus 1 dx. I always forget the little stuff at the plus 1 dx. The necessary guys, trust. Alright, so this, we can bring the a out, so it's equal to a of the integral u over u squared plus 1 minus a squared plus 1 dx. And then this, we can bring this whole thing out because none of these are with respect to the actual variable that we're integrating to. So it'll be b minus a little a of the integral of 1 over u squared plus 1 minus a squared plus 1 dx. Alright, these are both easy integrals. In fact, you should just have them memorized by now. And this is equal to, and this one should be easy. Let's do this, but it's just the natural log. So, and let's just do this one first. So it'll be b minus a little a of, and then the natural log of u squared plus 1 minus a squared plus 1 plus, see, but we're going to do that, plus, and this one is going to be slightly different, so it's going to be a, and then, so we're just trying to do an issue. It's not an issue, just another more carelessness. This squared is supposed to be on the inside for all of them. Just pretend that I don't know how to complete a square. It's very hard. It's not hard. Just basic stuff that I need to get good at. For some reason I'm out here doing this, not what I'm supposed to be doing. I have the geometry exam on tomorrow. I'm recording this on Sunday. Alright. The reason I say this is because this is actually supposed to be a variable. Just call it b. And so, then this is supposed to be arctangent. 1 over b, the arctangent of u squared. U squared over b. Very good. So this should spark you something crazy. So remember that this is equal to 1 minus cosine. Wait, what's cosine? Well, actually, we take the root square to this. Okay, sine. So let's do that. And this has to be equal to just b. And then inside of all here, you square them. Right? Let's do this is the square. And then plus c. Alright, so now we're going to have to figure out a substitution for a and b, and that part is actually kind of special. So let's get to that real quick. Let's just erase all this unnecessary stuff right here. Hold on, guys, there's more issues. Check my notes. These are supposed to switch. And this is supposed to go in half from natural log. Guys, I'm in geometry. Guys, give me a break, please. It's a miracle I can even do this. Okay, it's actually a over 2 ln u squared plus n b squared. Let's just do that. Plus 1 plus, and then it is b times a little a, and this is actually b, because I don't know how to integrate. I have my formula. I forgot my formulas. -1 u squared plus b plus c. There you go. That should actually be the correct. Let me just check one last time. Should be. I guess we can just undo the square, which will be x squared plus 2ax plus 1. And I guess that's just the best way. Alright. Back to how we're going to substitute a and b. Well, alright, okay, so finding y for a and the value for b. Alright, so that's it. What we're going to do is we're going to compare this with the final formula. Alright, but obviously, because then we can just compare and we can plug in a and figure out what will be equal to that. Because we actually have the formula. We're trying to devise, right? We're trying to figure out where it came from, so we don't need to brute force it. But yeah, this is the formula right here, right? Let me write that out real quick. And I'm going to leave out the sum because I'm only just going to be comparing these parts with this part. Alright, I believe this to be the formula right here. So first, let's compare. So, we know that this part corresponds to this part, right? A over 2. So, let's say that a over 2 corresponds to cosine of theta. And so, a would correspond to 2 cosine theta. And then what about right here, though? This would be 2 cosine squared theta. And do we see that anywhere in here? So first, let's compare this. So, natural log right here. Boom. Plus 1. Plus 1 plus what? Plus, there's no 1 here. This plus 1, so that 1 here. And then plus b times this. Alright. And then that means that b minus a little a, b corresponds to 2b. These are exactly the same. These correspond to each other. This corresponds to this, and this corresponds to that. Let me just make sure that my formula is written correctly. 2, okay. Yep. Alright. So let's now solve this. Alright, so we can multiply the both sides, so. Yeah! B minus a little a is equal to 2b squared. Alright, now you know that a corresponds to this, so we can plug in a, so we have b minus, and then the other way, so it will be, and then 2a squared is equal to 2b squared. I hope I'm doing this correctly. I don't really do partial fraction decomposition when I integrate, because I normally don't have to integrate stuff like this. Alright, that means that now that b can subtract, so b is equal to 2a squared plus 2b squared. 1 over the n in the front of this right here, right? So that means we're going to have 1 over n in here, right? Which does change this. So actually, both of these are 2 over n. So it'll be 2n right here and 2n right here, because this is also 2 over n. Right? Yep. Alright, and now I believe all we have to do is just plug in. Basically, we know that a little a minus b over b, right? this to be the case. Yeah, it is. It's just the other way around. B minus a little a is equal to 2b. And now we can solve. All right. So first we can always multiply inside of b. So b minus a little a is equal to 2b. 2b squared, that is. And then we can now subtract both a. So b is equal to a little a plus 2b squared. And let's say that's equal to, b is equal to 2 and cosine squared theta plus 2 sine squared theta. Well, that's the second thing we got. Is that not what I just did? I might be losing my mind, guys. I might be losing my mind. Either way, we know about A for B. We know that it will simplify into 2a. Alright? Because, watch. Let's say that 2 over n cosine, let's just do a squared. A squared plus 2b squared, and this has to be, actually, n over 2 squared, I remember that. Cheeky little 1 over n. 2 over. Alright, and now let's put this in. So, minus a, minus, then it's a. I think that's what I forgot to do when I was simplifying it. I think that's actually what it was. So 2 and a squared is equal to 2 and b squared by both sides by b. B, boom. Blah, 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 blah. We're done. Alright. Now let's write out the final thing. Okay, so I'm just going to write it out right here because I'm kind of running out of room. Actually, no, I'm just going to write this right here. B is equal to n over 2a squared plus n over 2b squared. That's not in the simplified way, but don't worry. Okay, so now we have cosine theta is n over 2 cosine theta, but then this cancels out, so it's just cosine theta. Natural log of x minus 2 cosine theta x plus 1 plus, and then this simplifies, so it simplifies to this, so this is going to simply be n over 2 b squared plus arctangent of x plus a over b. And let's write this out as a full sum now, since we can. We cannot forget the 1 over n in the front. N over 2 minus 1 k is equal to 0 of cosine theta of the natural log of x squared minus 2 cosine theta x plus 1 plus, and then since this out is just sine, since yeah, b was the square root of this, so it's just sine. Yeah, let's do sine now. Sine theta plus the arctangent of, and then x plus a, so it'll be x plus cosine theta over sine theta. And let's not forget, theta is equal to 2k plus 1 pi over n. And there we have it. There's the formula. Hold on, my phone's about to die. We have the formula right there. And obviously, n is even. Boom, there's actually, and why are we doing this? Well, it'll fit in, trust me. I believe that my professor has put that in strategically to help me, even though, I don't know, my professor's kind of weird. He like once just bought a ton of oranges, and he didn't eat them. He just like put them in a box, then he counted them over and over again. That was kind of weird. Yeah, but there we go. Let's do the thingy. Alright, I hope you enjoyed.